On our last part of the series, we finished all of our opcodes, but now we actually need to start doing our video rendering. Here in our case, for the opcode D, our actual video logic will be called here, but we're going to make a separate helper function and we're going to put our code in there, so then all we need to do is just put a call to that function here. So we'll start in the header file. I'm going to make a function called drawSprite. We'll pass our CPU pointer parameter, pass a value for X coordinate, we'll pass a value for Y coordinate, and we will pass a height coordinate, which we will explain later. Let's go back to our cpu.c file and find the D instruction. We'll go ahead and set this up now, so then later we can just write our code for drawSprite and everything will come together. We can make our call to drawSprite here, pass our CPU pointer, pass the X coordinate, pass the Y coordinate, and then pass the N coordinate. And this is all we're going to actually need in the instruction case. The rest of it's going to be handled in the helper function itself. A little note before we begin, this part can get a bit confusing if you've never done this kind of thing before. Take your time, go through each and every line, and make sure you understand what every line is doing before you actually write it out. That way you'll get an idea of what we're actually doing in STL, which is going to be our program where we render all of these pixels at. For now, we'll stay focused on the drawSprite function. We'll get that done, and then everything else will be a lot simpler once we already have our logic ready to go. We'll go ahead and write out our drawSprite function. And the first thing we need to do is we need to grab our coordinates from the actual V registers themselves. So the way that we can do that is we can declare two 8-bit values. First one we'll call it X position, or I'll call it XPOS. And we need to call the register at X. But here I'm going to do something a little bit different. I'm going to do some modulo math, and we're going to do a modulo of 64. And the reason we are doing this is because we want the pixels to wrap around to the other side of the screen instead of drawing off the screen. We'll do a similar thing here with the Y position, but instead we'll do it with modulo 32. This time we'll grab V with Y, modulo 32. These two numbers come from the fact that the Chip8 resolution is 64 by 32 in standard mode. Later on we may implement the high res mode, and if we do that it'll be 128 by 64 instead. Moving along, the next thing we'll do is we will set the actual flag register to 0. And the reason we're doing this is because it's going to act as a collision register, so we can tell if pixels are colliding on screen. This needs to be reset to 0 every time we draw the sprite, so then we can use the logic later to find out if there is a collision or not. The first thing we'll do is we'll start iterating over our rows and columns that we need. We'll start with our rows. The reason we needed that H parameter before is the instruction will tell us how tall the actual sprite is that's being drawn, so we can use it as a comparator here for row so we don't go over that limit. We can get our actual row from memory now. I'll go ahead and make a 16-bit unsigned integer. We'll call it sprite byte. We'll point into memory. We'll point to our index, and then we'll add the row count. So each byte is going to represent one row of the sprite, and we can iterate through it by using this line. And from here we're going to need to go through our columns. So we can make another for loop in here. Also an 8-bit unsigned integer. We'll call it call for column. Start at 0. And now we need to loop through the 8 columns in that byte. Or bits rather, so we'll just say column has to be less than 8, and then we'll increment. So now we need to read our bits from left to right, so we're going to go ahead and make another 8-bit integer here, and we'll call it sprite pixel. What we're going to do is we're going to take the most significant bit first, and we're going to go down the line to the right. So the way that we can do this is we can take our sprite byte, we can shift it to the right by 7 minus what our column is at right now. And the reason we do it this way is because we're reading from left to right. And then from there we'll mask off using 0x1, and that will get each of our bit in each location, starting from the most significant from the left to the least significant bit on the right. Now, of course, we only need to draw the pixels that are actually on, and the ones that are not, we can just ignore. So we'll put an if statement here. This will tell us if the sprite pixel is indeed on. We'll make two 8-bit integers here. First one will be px for pixel x. We'll take our x position. We'll add our column so we're in the right position. And we'll also modulate this by 64. We're going to do the same thing with py, but y position with the row, and our modulus is going to be of 32. Lastly, we'll need our index for our frame buffer, so we will make a 16-bit integer. I will call it fb for frame buffer, idx for index, equals py times 64 plus rpx. Let me do an explanation on these so everyone understands. This first line and the second line, all we're doing here is just calculating the actual screen position with our wrapping, so we understand that when it reaches a certain point it wraps around to the other side of the screen. The frame buffer IDX, what this is doing is we have a two-dimensional screen, right? We have our X and our Y, but our frame buffer is only a one-dimensional array. This allows us to have a one-dimensional array rather than a two-dimensional array, which not only saves us memory, but I think it makes it less complicated because the CPU is doing more of the actual math work than we would be. Now, before we toggle our actual bit on or off, we need to do a flag check. So what we're going to do is we will check the CPU frame buffer at the index. And we need to check if it equals 1. If it does, then we know that there was a collision. So we can take our flag register at V, and we can set it equal to 1. Now the last thing we need to do is actually toggle our bit on. We can do that with an XOR. Make sure to do it at index. We can set it as XOR equals 1. This will toggle the bit if it's off, and it will turn it off if it's already on. Okay, I want to go over this function so everyone understands exactly what we are doing here. The X and Y position are the first things we calculate, and we calculate it based off of the X and Y coordinates that the instruction gave us when it was called. Then from there, we set our collision register to 0. We iterate through our rows, and we grab the sprite byte, and our columns, which we grab each pixel from that said byte. If the pixel is on, then we take the px and py, which is basically just the coordinates again, but what we're doing is we're taking the base coordinate, which is our x position, adding the column because that's where we're at right now, and the y position and the row because that's where we're at right now. And we keep our wrapping here in case it draws off screen. For the frame buffer index, this is the part that trips most people up when I teach this. This is just a flattened array formula. So this formula follows the same guidelines, and I'll make a comment of it here. The formula is our index is going to be equal to the row times the number of columns plus the column itself. So we know that from the py, we know that's our current row. And we know that we have 64 columns because that's the screen size. And then we just add our current column back. This is called flattening an array, and we're flattening a two-dimensional array down to a one-dimensional index. This is a great way to keep everything in one spot rather than having a two-dimensional array. And like I said before, I prefer the type of programming where the CPU does the work for us, the CPU putting in the actual mathematics rather than us coding everything from scratch from the two-dimensional array. Now that the math here is finished, everything else is straightforward. We just check the frame buffer. If it equals 1, we know there was a collision. We just set the flag register to 1, and then we toggle the bit as needed. So remember, this is a toggle. If the bit is already 0, it will turn into 1, and if it's already 1, it'll turn into 0. I wanted to keep this part short because I know the math on this part can be a bit confusing, so if you have questions, please feel free to ask. For the next part, I want to focus on primarily getting STL up and running so we can take this draw sprite function and actually start drawing stuff on the screen. Take some time to review this and make sure you understand how this works. It makes a lot more sense if you understand each and every part the way that it's written here. That being said, if you have any suggestions on things that I should change or maybe to explain better, please let me know and I'll do my best to go over it in one of the future parts. I appreciate you guys for coming. Have a good day.